Welcome back to the channel. Today is lecture 3 of waves. I'm sure you have gone through lecture 1 and lecture 2 in which we define waves. We formulated the general equation of a plane progressive harmonic wave. And in today's lecture, we'll talk about phase and phase difference. This is a very important and many times neglected topic, so pay close attention. Okay? Okay. So this is the equation of a plane progressive harmonic wave. Y, which gives the disturbance, in our case we'll assume this as displacement, is amplitude times sine omega t minus kx plus phi. Okay. So quite a bit of information we can figure out from this. One, this wave is traveling in the positive x direction. It has amplitude a. We can find out the speed of the wave, which is coefficient of t divided by coefficient of x, which is omega by k. Omega gives us information about the time period. So omega is 2 pi by time period t, and k gives us information about the wavelength of the wave. K is 2 pi by lambda. Okay, so all of this has been discussed in previous lectures. So if you're unfamiliar with that, I will encourage you again to check out wave 1 and wave 2 lectures on the channel. Okay. All right. So this is our disturbance, and let's say this is our x coordinate, which is the wave is traveling along the x coordinate. Okay. I will also draw disturbance y versus time graph. So these two are important graphs. Okay. So even before plotting anything here, let's just imagine or try to understand what these graphs represent. So when we draw y versus x graph, we are fixing time, right? We are looking at how the displacements along different points in the medium in the direction of wave travel is changing at a particular time. So that's why time is fixed. You can imagine this as a snapshot. By snapshot, I mean you take a quick picture or a quick snap of the wave at certain time. Okay. Now, when we plot y versus t, what we are doing is here we are focusing on maybe one of the particles in the medium in which the wave is traveling. So maybe at x equals 0 or maybe at x equals at some other point. So we are fixing x. Okay. Here time was fixed, here x is fixed. Okay. So x fixed means we are now focusing on one particle only. Now once we have focused on that one particle, now we are taking a video, which means we are looking at how that particle's displacement or disturbance is changing as time progresses. So this is no more a snapshot, this is like a video. Something that is moving, something that is changing with time. That's why we plot y against t. So first thing in these concepts, make sure you understand what you are looking at. If it is a y versus x graph, then time is fixed. If it is a y versus t graph, then we are fixing a particle. X is fixed. Okay. Now let's try to plot this at some fixed time. Okay. Now before we plot these graphs, let me explain what is a phase. Everything that is inside this bracket, inside this sign function, is called phase. Okay. What is phi in this case? Phi is the initial phase of source particle of x equals 0. If you put x equals 0, time equals 0, so that's why it's called initial phase of x equals 0. Okay. Most of the time we will assume the initial phase to be 0. So this function will then reduce as y equals a sine omega t minus kx, assuming that the initial phase is 0. Okay. Now let's consider this case. We have fixed time, so we are taking a snapshot. So maybe I will write this here. Okay. So if we fix t, let's suppose t is fixed at time period by 2. We can fix any t. For my convenience, I just take time period by 2. Okay. So then what happens? Before we draw this function, let's substitute t equals t by 2 here and see what happens. So y is a sine omega t. So omega is 2 pi by t times t is t by 2 minus kx. So t gets cancelled, 2 and 2 gets cancelled. A sine pi minus kx. So pi minus kx is 180 degree minus some theta. So it is in the second quadrant. In the second quadrant, sign is positive and it does not change. It remains as sine. So this becomes a sine kx. Okay. Further, we can also write this as a sine, substitute value of k, which is 2 pi by lambda times x. Okay. Now, it's easy to draw the graph of y equals a sine 2 pi by lambda x. So let's do that. So since this is sine and at x equals 0, it will be 0. And as x increases, sine will be positive, and so my graph is something like this. Okay. So this maximum amplitude is A. Okay. And at x equals 0, it's 0. At what x will this be 0 again? So at lambda by 2, this becomes sine pi. So this is lambda by 2. This is lambda. This is 3 lambda by 2. Okay. At what value of x is y maximum? It is lambda by 4. Because at lambda by 4, this is pi by 2. So this is 3 lambda by 4. This is 5 lambda by 4. Okay. Now, for convenience, I will just say this is equals to phi. So don't confuse this by this initial phase. Maybe we can just make this phi 0, phi naught, to make sure that's initial phase. So let's just say omega t minus kx is phi, which is the phase. That's what we talked about. Okay. At some x1, phase is phi 1. At some x2, phase is phi 2. Okay. At some x, phase is phi 1. This is the phase. At some other x value, phase is phi 2. Now we can say the distance difference, delta x. This is what distance difference. Okay. So if I am considering a point here, another point here, so this is the distance difference. Okay. So distance difference is x2 minus x1. Corresponding to this distance difference, what is the phase difference? That's how we define phase difference. Okay. So phase difference, or we can say phase difference between these 2 points at a time is what? So it's easy. So phi 1 is omega t minus kx1, and phi 2 is omega t minus kx2. Obviously, since we are doing t is time period by 2, so we can substitute that. But in general, for any time, if we are looking at x1 and x2 at a particular time, then this is what it is. So what is delta phi? Delta phi is phi 2 minus phi 1, or mod of phi 2 minus phi 1, whichever way you look at it. This is k x2 minus x1. Let's just imagine its mod. Okay, so this is k delta x. So now we get a relation. Phase difference is 2 pi by lambda into distance difference. Okay. So if two particles at a given time is at a distance lambda, let's say. So this particle and this particle are at a distance separated by lambda. Let's write those down. Maybe we call this point A, point B, point C, point D, point E, F, G, and such. Okay. So now let's look at this. A and E, the distance difference is lambda. Then what is the phase difference? Is 2 pi. Okay. A and C, the distance difference is lambda by 2. Then what is the phase difference? It is pi. Okay. Now, looking at these different points at a given time, which ones should we say are in the same phase and which are in opposite phase? So this is the concept of same phase and opposite phase. Okay. Two particles are considered to be in the same phase if their displacement, their velocity vector, and their acceleration vector are all same. So we are comparing vectors, which means magnitude and direction must be same. Let's look at this. A is displacement 0, C is also displacement 0, but velocity wise, where is A trying to move? Is it trying to move up or down? Remember, in the last lecture, we devised something like this. Velocity of a particle is negative of wave velocity times del y del x. Do you remember that? So we have the yx graph. If del y del x, which is the slope of this graph at a point, if I draw a slope, it will be like this, which is positive slope. Positive slope and velocity vector is in the positive x direction, so both are positive. Which way is the velocity of the particle at A? It is going down because it's negative. So here the particle, if I draw the velocity direction, in the next instant it is trying to move downwards. What about C? Where is the particle trying to move in the next instant? Here, if I draw a slope at point C, it is negative slope. Negative times negative is positive. This is actually trying to move up. So can we say A and C are in the same phase? Although their displacements are same, which is 0, although their magnitude of velocities are same, but their directions are opposite. So A and C are not in same phase. Okay? We're just talking about velocity right now. Then we'll talk about acceleration as well. Now, if I look at E, E has positive slope, so which means velocity vector is downward. So A and E could be in same phase. Let's look at acceleration. Similarly, in the last lecture, we talked about acceleration of a particle is minus omega square ay. Acceleration at point A is 0, y is 0. Acceleration at point C is 0. So acceleration we do not have an issue with. So A and E we can say are in the same phase. So A, E are in same phase. Then next time when it crosses again, it will be in the same phase. So these are in same phase. We can say C and G are in same phase, because why? G, if I draw a tangent here, the slope is negative. Negative times positive is positive. So this one is also trying to move up. So C and G are in same phase. C and G are in same phase. Okay. Similarly, you will be able to figure out that B and F are in same phase. Okay. Okay. So you will see that the phase difference when two particles at a given snapshot are in same phase, they occur, these two occur when A and E occurs at lambda difference. So lambda means 2 pi. So phase difference is 2 pi. Next time that it will happen will be 2 lambda. So that will be 4 pi, 6 pi onwards. Okay. Also we can say this, the phase difference happens at what distance differences. So 2 pi means lambda, 2 lambda, 3 lambda and such. Okay. All right. Hope this is clear what same phase means. Now what is opposite phase? Opposite phase is when two particles at a given time, they have the same magnitude of displacement, velocity and acceleration, but their directions are opposite. Okay. So we can clearly see A and C are in opposite phases. Similarly, C and E are in opposite phases. We can say B and D are in opposite phases. Okay. Now, if I look at it in terms of, so this was in terms of phase difference, this was in terms of distance difference. In terms of phase difference, at what intervals opposite phases happen? So A and C, right? So lambda by 2. So lambda by 2 means pi. Next time when it will happen, so A is in opposite phase to C, A is in opposite phase to G. So the next time it happens is 3 lambda by 2. So 3 lambda by 2 will be 3 pi, 5 pi and such. Okay. So particles in opposite phases happen at difference of phase difference pi, 3 pi, 5 pi and such. If I look at the distance difference, then they occur at intervals of lambda by 2, A and G is 3 lambda by 2. So lambda by 2, 3 lambda by 2, 5 lambda by 2 and such. Okay. All right. So this is an important result that we got for different particles at some time t1. Okay. Now let's try to do the phase difference for the same particle at different times. So first let's write down that relation that we got, phase difference of two particles at the same time is 2 pi by lambda multiplied by the distance difference. Okay. This is for different particles at the same time. Okay. Now we are trying to do this. We are focusing on one particle at different times. Okay. So how can we draw that graph? So we can take up any particle. For our convenience, let's take up the particle at x equals 0. Okay. So if I take up the particle at x equals 0, then my equation now becomes y equals a sine omega t, or we can say y equals a sine 2 pi by time period times t. Okay. Now at t equals 0, sine is 0. So the sine curve will be similar to this. We will start with this. So let's draw that. Okay. So this is again maximum amplitude is A. This is at time t equals 0. At what time will sine be 0 again? So sine will be 0 at pi, so at t by 2. So this is at t by 2 it is 0. Again at t it is 0. Again at 3t by 2 it's 0. Okay. At what time is value of y maximum? It is at when this value is pi by 2. So that will be at t by 4. And that's obvious from the graph as well. So this is t by 4, 3t by 4, 5t by 4, and such. Okay. Now let's assume at some time t1, this source particle at x equals 0, okay, for which I am drawing this y by t graph, at some time t1, the phase was phi1, and at another time t2, the phase was phi2. Okay, what is phi? Again, everything inside this bracket is called the phase. That's what it is. Okay, so we can write the phase difference delta phi, or in fact, let's write phi 1 first. Phi 1 is omega t1 minus kx. Now it can be any x. We took x equals 0 for our convenience, but it can be any x. Phi 2 is omega t2 minus kx. So the change in phase delta phi is phi 2 minus phi 1. If we take mod of everything, so this becomes omega t2 minus t1. T2 minus T1 will call this as time difference, which is delta T. So now we can write phase difference is equals to omega delta T. Omega is 2 pi by T delta T. Okay. Now this is applicable for the same particle at different times. Okay, let's write that down. All right. Okay. Now let's consider time at A, at B, at C, at D, at E, at F, at G. Remember, these are all the same particles at different times. Now, at which times is that same particle in phase and in opposite phase? Again, the definition of same phase remains the same. The same particle, when it has the same displacement, same velocity, same acceleration in magnitude and direction at two different times, then those two different times are in same phase. If all these quantities, the displacement, velocity and acceleration have same magnitude but opposite directions, then those two different times are in opposite phase. Okay, so make sure your concept of same phase and opposite phase are clear. Now, can two different particles have to be in same phase and opposite phase? No, not necessarily. Two particles can be neither, or same particle at two different times could be neither in same phase or opposite phase. Okay, so this is a special name given to two different conditions when displacements, the velocities and the accelerations are either all are same magnitude but in the same direction or in the opposite direction. Okay, so now let's look at this. So this is actually much simpler because this is nothing but simple harmonic motion. For one, when we are looking at one particle, this is simple harmonic motion of one particle. So we know A, C, E, G, they are all in zero displacement. At the mean position, acceleration is also zero. At the mean position, here the velocity is maximum towards the positive direction. Here the velocity is maximum towards the negative direction. So same phase, we will say A, E, then the following one will be in same phase. Similarly, C and G will be in same phase. Similarly, B and C and G will be in same phase. Yes. B and F will be in same phase. Okay. All right. So the same phases will happen at T, 2T, 3T, like that. Actually, we should start with 0. 0T, 2T, like that. So this is delta T. And from the value of phi, so 0, when it is T, it is 2 pi. When it is 2T, it is 4 pi, 6 pi, and such. So this is delta phi. Okay. How about opposite phases? A and C are in opposite phase. A, C, again G. So how often it is repeating? That's what I am trying to find out here. Similarly, C, E, these are opposite phases. B and D are in opposite phases. You get it, right? For both B and D, the displacement amount is same but in opposite direction. Velocities are 0 in both. The accelerations, for B it is some magnitude towards the mean position, for D is the same magnitude in the opposite way towards the mean position. So B and D are in opposite phases. Okay. So this one happens A, C, T by 2, 3T by 2, 5T by 2, and such. So this is delta T. Corresponding delta phi is pi, 3 pi, 5 pi, and such. Okay. So now you know what is a phase. Second, you know the phase difference for different particles at the same time. You are looking at a y-x graph. for phase difference for same particle at different times, you are looking at a YT graph. Okay. Now, this phase differences, how we defined those was for the same wave. Same wave, we can find out the phase differences between two different waves. Let's look at that now. Okay, we'll look at two different things now. Let's say we have the same wave, okay, and the other case we'll look at are two different waves. Same wave, if we look at two different points, x1 and x2, at two different times, let's say x1 we are looking at it at t1 time, and x2 we are looking at it at t2 time. Okay. Then what is the phase difference between these 2 points separated by some time? Great. So I know my phase is omega t minus kx. So first phase for the first particle would be omega t1 minus kx1, and phase 2 of the second particle at a different time, omega t2 minus kx2. Now if I calculate the phase difference delta phi, which is phi 2 minus phi 1, we will get omega t2 minus t1 minus k x2 minus x1. Okay. So the concept of phase difference is actually very simple. It is just the difference of the phases. Now special conditions when x2 and x1 are same, which means we're talking about the same particle at two different times, then we get delta phi equals omega delta t, which is 2 pi by t delta t, when x2 and x1 are same. So what is this? We are looking at the same particle at two different times. Now if we are looking at two different particles at the same time, then delta phi becomes, so this becomes 0, omitting the negative sign here, k, which is 2 pi by lambda delta x at the same time. So t2 and t1 are same. This is the results that we got, okay, and we understood that in a little bit more detail using these two graphs, okay. All right. Now phase difference between two different waves. This concept will come in handy when we study interference. So for different waves, let's say wave 1's function is y equals a1 sine, it could have a different omega 2, omega 1 t minus k1x. And wave 2's function is y equals a2 sine omega 2t minus k2x. Let's say we can denote this as y1 and this is y2. Okay. Now let's say these two waves, they collide at a point. Okay. By principle of superposition, the y net, the net displacement at a point where they are colliding or interfering, is given by y1 plus y2, the vector sum of these two. Let's say these are collinear waves, which means they are traveling in the same direction or opposite directions, so that the y's are in the same, the displacements are in the same direction, then it is just y1 plus y2. So y net we will write then as a1 sine omega 1 t minus k1x plus a2 sine omega 2t minus k2x. If we can represent this as something like a net sine, so here I made a mistake, y net a1 sine omega t, here x is no more a variable because if two waves, let's suppose there are two waves, one traveling this way, another traveling this way, and they collide at a point P. For this y1 wave, this distance is x1, y2 wave, this distance is x2. So we are in effect doing the net displacement at P, so which means we should write this as x1 and x2. We are not generalizing it, it is at some point, so x's are fixed. Okay? Okay. Another problem with this one is if omega 1 and omega 2 are different, then they are incoherent waves, which means their frequencies are different. If we also assume that they are coherent waves, which means omega 1 equals omega 2, and let's just write that as omega, then this can be reduced to something of this form, a net sine omega t plus theta. Okay, and A net can be found out as A1 square plus A2 square plus 2A1 A2 cos delta phi, where delta phi is 2 pi by t, which is omega, times x2 minus x1. This is applicable only if these are coherent sources, which means both these waves have the same frequency, and delta phi will be this. So you will see that the net amplitude at the point is a function of phase difference. Here the phase difference is still between these two waves is still this phase minus this phase, which is what? Omega 2 minus omega 1 t plus minus, we can write k2 x2 plus k1 x1. If both were coherent, then this term will be 0. So the phase difference will not depend on time if both are coherent. And if k2 and k1 were same, which is their wavelengths are same, then phase difference is only 2 pi by lambda x2 minus x1. I made a mistake here, this should be 2 pi by lambda. Okay. We will discuss this in detail when we talk about interference, but what I wanted to highlight here is the definition of phase difference remains the same. Phase difference is difference between the phases. Why this is important in interference is because the net amplitude, we will show that it depends on the phase difference, and if the phase difference is only dependent on the path difference, this is now called path difference because these are for two different waves, path of two different waves. Here we don't call delta x as path difference, that is distance difference, because it is, we are talking about the same wave. But here, if we are talking about two different waves, then we can call this as path difference. Okay, so anyways, regardless, we'll talk more about this in detail in interference, but now you should have a fair idea of what is a phase and what is phase difference. Okay? All right. So with that, we'll close this lecture for today and we'll take up interference in the next one.